There is a force pushing on the sail that's exerted by something that has zero mass, electromagnetic radiation, or light. Just like molecules of air can push the sail, light can also move objects. So does that mean, with this flashlight, I can supercharge my boat? Okay, yeah, so shining a flashlight on my boat isn't going to help me move it much faster. Light pressure is super tiny. The force exerted by 1 square meter of sunlight is even less than the weight of a grain of sand. But with the proper adjustment of variables, light pressure is strong enough to move even spaceships. Let's see how. First, we have to ask, how can light push on something at all when it doesn't even have mass? Well, light is energy, and when we look at the full version of Einstein's famous equation that accounts for objects in motion too, E squared equals mc squared squared plus p squared, where p is momentum, we find that energy for something massless is momentum times the speed of light. So the momentum gained by an object that absorbs light is energy divided by the speed of light, and light's energy is intensity times area times time. That's going to be important. Intensity is like the concentration of light. Imagine the points in this balloon are light rays. At the source of a light, intensity is really high. You can tell by how densely the points in the balloon are packed. The closer the light rays are to the source where it's emanating, the closer the points are to each other on the balloon, and the more amount of light there is in a certain space. The second variable is area. The larger the surface area of the object, the more light is going to hit it. See how in the smaller area there are fewer points of light than in the larger area. And the third variable is time. Simply put, the longer an object is around to get hit by light, the more light is going to hit it. Whether increasing intensity, area, or time, the object in question is going to get hit by more light, and in turn, get more momentum. A more reflective surface gains even more momentum than an absorptive one. This is because the total amount of momentum in a system always remains the same. Let's take a look. Let's say that this tennis ball is a pulse of light and that it has momentum p. When an object that completely absorbs light collides with light, the object completely gains the light's momentum. So before and after the collision, the total momentum in the system is still p. When an object that completely reflects light collides with light, light bounces off in the opposite direction, with its momentum reversed to be negative p. But because the total momentum of the system is always the same, the object is going to start traveling with the momentum of 2p, and the total momentum is still just p. So a perfectly reflective object gains 2 times the momentum of the light that hits it. Okay, so imagine if we took our boat to space. If you increase area by making the sail huge, increase intensity by traveling close to stars, and increase time by sending the ship over astronomical distances, and double it all by making the sail reflective, the momentum passed from light pressure is large enough that our ship can sail through the stars.